It's okay.
Great. So please try to stick to the time. 15 minutes for the talk, 5 minutes for discussion. Thank you. Please.
Okay. Well, first of all, I want to thank the organizing committee and in particular to my advisor, Professor Alfaro, for giving the opportunity to give this talk among all of these world-class researchers. This is a small project I want to share. I did it by my own at a couple of months ago, and recently I received the notice that it was accepted for publication in the Physics Diary of the Universe um, journal. So I am a little happy. Um, I'm going to talk about inflation. Um, in order to be in time, I'm not going to do a very long introduction. Inflation is this model proposed by many people in the 80s by Alan Good, Stravinsky, Linde, and many others that tries to solve the problems of Big Bang, the standard Big Bang theory. For example, the horizon problem, the flatness problem, etc. This is a model that implies an exponential rate of acceleration of the universe shortly after the Big Bang. And the simplest way to do that is adding a scalar field, a single scalar field, minimally coupled to the curvature. And this is the simplest inflationary model that we can have. And when do we do that? Um, you use a specially homogeneous field described by this Lagrangian. We have the Friedman equations when we um, replace the Einstein field equations. So the first one is the first Friedman equation. The second one is the acceleration equation, which gives us the dynamics of this field which we called the inflaton. Um, when we vary the action with respect to the field, we obtain the Klein-Gordon equation of this field and coupling with the Hubble parameter. Um, in order to have inflation, we need to impose a condition. In order to have a quasi-exponential rate of expansion, we can take the derivative of the inverse of the Hubble parameter to be much less than 1. If that did happen, we have this slower condition. This is well-known condition to have inflation. Basically, it says that the potential part is much important, more relevant than the kinetic terms. Um, and to use this condition, we can approximate some parameters and have a more easy theory to work. The first one, the first parameter is the epsilon, the first slow roll parameter. It is actually defined as the time derivative of the inverse of the Hubble parameter. Um, and when we use the slow roll condition, it is approximated um, to this term here, which is the epsilon sub b. And this is a parameter that depends only on the potential and its derivatives. The same thing we can do to define the second slow roll parameter, the eta. If we take the time derivative of the epsilon, we can define an eta. And using the slow roll condition, we arrive to the second slow roll parameter depending on the potential and in this case, the second derivative of the potential with respect to the field. Why I say that and why these parameters are important, because we maybe all know with these parameters we can define the spectral and the tensor indices. And these indices, n sub s and sub t, are related to the tensor power spectrum, which is observable and is usually what the missions like Kobe or Planck observes in the CMB. And also we can write the number of e-folds, which is defined as the natural logarithm of the scale factor um, in terms of the potential um, and its derivatives. So uh, what I'm going to talk now, it's F of R gravity. This is a model proposed by Harco in 2011, and it is widely studied for many researchers around the world. And I look it and I found it interesting, and I realized that nobody worked on inflation in this theory, so I tried to to do it by myself. Um, this is a model described by the action 14. This is basically a generalization of the F of R gravity. In this case, we add the not it is a function, not only a function of the scalar curvature, but also a function of the trace of the energy momentum tensor. If we variate the action 14 with respect to the metric, we obtain the field equations. In this case, we obtain a term theta, which is defined by the equation 17. And we define the energy momentum tensor as usual, as the variation of the matter Lagrangian of the action. So in this particular work, we consider this functional form of the function f, and is the minimal coupling between matter and gravity, and it's the simplest model we can work on. The equations of motion can be cast in this form, in the form of equation 18. It's basically it is very similar to the equation of the Einstein equation, but in this case, the effective there is an effective energy momentum tensor given by equation 19. Um, and this equation, you can see that there is a correction to the standard effective energy momentum tensor, which is given by the second term in the brackets. We can define using the prescription of using an especially homogeneous scalar field. And when we do that, we obtain the effective energy momentum tensor given by equation 21 and 22. And we can see that this tensor is diagonal as the standard one. And also we can define something like the energy density, the effective energy density, and an effective isotropic pressure uh, in the same way we do it in the scalar field. Um, we can also define an effective equation of state, dividing the pressure by the energy density, and we see some similarity with what happened with quintessences. So, uh, following the same procedure than the standard general relativity, we can obtain the Friedman and Klein-Gordon equations, which are given by equations 24, 25, and 26. And we can see here that the correction to are given basically by these terms proportional to alpha, which is the coupling that the coupling between the gravity and the matter. Um, so this alpha term would imply some correction to the slow roll parameters. Actually, the slow roll condition is also modified by equation 27. Um, then we can define, and following a similar procedure, to define epsilon and eta, the two first slow roll parameters, and the number of the e-folds can also be defined and is modified also by this term, including the alpha term. So in general, what we have is a theory that have corrections to all the cosmological parameters. That could be imply corrections to the observable objects, for example, the spectral indices. So that is why I wanted to look. Um, and here's this, there's an important thing to say. I realized that this model is equivalent to a scalar tensor theory of gravity. For example, we have the general form of equation 32, and we can prove that this action is equivalent to the action of F of R and T gravity if we choose the following particular choices. Um, that is a very important thing to say, because we can recast this action um, as a scalar field minimally coupled to the general relativity, which is the Einstein frame. It is known as the Einstein frame. And with that, we can define something like an effective potential that can give us some hints about the dynamics of the potentials of usual or standard models of inflation, but with this contribution, with uh, this modified model of gravity. And an effective potential is given by this expression in equation 33. um, what I have did, I applied this prescription on several models of inflation. The first one is the power law potential, basically the most simplest model of inflation, a potential which is a power law. Um, when I compute the slow roll parameters, I obtain this expression in equation 35. And after following the procedure, the standard procedure, I obtained the spectral indices. And what I have realized is that these indices are not affected by this model. So this model cannot solve the problems of power law potentials have, in particular with the phenomenology of inflation, and the measurements of Planck in 2018. Well, power law, nothing interesting happened. What happened with natural inflation? Natural inflation is a model whose inflaton field is a pseudo-Namu-Goldson boson produced by a spontaneous symmetry breaking added with an explicit symmetry breaking. It's a very interesting model developed in the 90s. Um, and this is a model described by this potential, the potential given in equation 39, where F and lambda are mass scales. These scales can drive inflation if are in um, some particular values, for some particular values. And I did the same procedure to compute the slow rock parameters in 40 and 41, equation 40 and 41. um, and in this case, the result is quietly different, but from the power law potential. The observables, which are the spectral indices, depends on the alpha. So here is a clear modification to these predictions by different values of alpha. Um, Actually, what I can do is to solve the error, which is the tensor to scalar ratio, in terms of n sub s, which is the scalar spectral index, and I can plot this on the error on an s plane, which is something that Planck mission did, and I'm going to show that that plot and in a couple of minutes.
So,
So
Mauricio, can I use that opportunity to say that you're speaking for 15 minutes now? Just so you're
yes, I
aware.
have 14 now. Yes, I have a chronometer. I have
Okay.
time, so I will be quick. I did the same within hilltop inflation, um, and the result is basically very similar. And there are similarities between those models. The main contribution can be enclosed by the following changing. The affection, so the modification of this model of gravity is changing the mass scales of the model, of the theory, of the in natural and heat inflation. I can well, we can see here the plots of the potential and how they change by changing the value of alpha. Um, so the last model I want to show you is the Starobinsky inflation model, given by the Action 50, one of the first model of inflation and one of the most successful model of inflation. Um, this model predicts the following spectral indices and the tensor to scalar radio in equation 51. I did the same following procedure. I compute all the thing, and we can see in equation 52a and 52b that it is also a modification. And in this case, there is no mass scale. So it is a direct modification on the prediction of Starobinsky inflation. Um, and that is very important. We can see here in 53 and 54 the potential of the Starobinsky inflation, which is basically the well-known form of slow roll inflation. It is also affected. The plateau of the potential, the height of the plateau of the potential is shifted by changing the value of alpha. So there is a direct modification due to this model. And this is the most important plot that I want to show you. This is the marginalized join 68% and 95% of the blank data given in 2018. We can see the shaded regions are what blank constrained values of the tensor to scalar radio and the scalar spectral index. And the stars are the limits of the prediction of the potentials of different models. And we can see here that the green, the light green line, which is the prediction of Starobinsky inflation, is shifted towards higher values of the tensor to scalar radio if we change the value of alpha. So uh, this model could modify the prediction of the tensor to scalar radio of the Starobinsky inflation model. And of course, that could be constrained more successfully if we have more information from, for example, for promoted gravitational waves or the VSEPs um, experiment. So the other models doesn't change the trajectory on the plane, but change the where it is plotted uh, each of these potential, and the power law potential has no any particular modification in this case. So this is summary. I don't want to I don't want to waste more your time, and I'm happy to be here. I'm happy to to show you what I have done, and thank you very much for your attention.
Thanks a lot for this talk. Let us see if there's one quick question, maybe.
Yeah, I have one. Can I?
You can either raise your hand or just.
I've already raised it.
Please.
Thank you.
Sorry, I didn't
Nice
see
talk. Sorry, that's all right. Nice talk. If you can you get more constraints by applying the Swampland criteria for embedding your models in quantum gravity, which are dealing with, as you know, first or second derivatives of the potentials, and they exclude many potentials. They exclude all the slow rolls, in fact. But can you get some constraints for your alpha parameter or other parameters?
Uh, I have not done that. I am not gonna lie to you, but I think it could be a good way to improve these results. I mean, this is the most fundamental and simplest test of these models. As far as I know, many of the quantum gravity models, for example, the symmetry breaking of supersymmetry, it is well outside the margins of the Planck, as in the um, more general models. So um, it could be thing. I maybe I should give a and give some thought about how can this could be applied to f of r anti-gravity. Um, I'm not sure how to do that. I want to be sure. I don't want to. I don't want to lie you, but
Okay, we're running a little bit late, and we also need to take the conference picture. I understand. Is there one of the organizers who's ready to do that?
I am. I will take picture.
Okay, so let's thanks again to Mauricio. Thank you.
Okay.